Welcome to this video on logarithmic functions. Here's a picture of me on top of a mountain, Mount Rundle, there by Canmore. Not sure what that has to do with logarithmic functions, but I thought it was a nice picture. Today's outcomes include things to do with logs. So graphing log functions, evaluating logs, converting between log and exponential equations, evaluating them using a change of base formula, and maybe looking at some applied problems that talk about logarithms. So today our main purpose is just to understand what a log is and a few useful tools to help us deal with logarithms. In future classes we'll see even more rules that we can use with logarithms. To begin with though, where have you seen logs before? You may have taken some chemistry classes in which they have used logs. One of them in particular is to determine the pH of a solution. To find the pH of a solution, you take the negative log of the hydrogen ion concentration. So if you know what this concentration is, using some kind of formula like that, not that you have to worry about that in math, you can find its concentration using this formula, including a log. You can determine the pH of a solution. In addition, things like the Richter scale, which is used to quantify or give us an idea of how effective or how big an earthquake was, is based on sort of a logarithmic kind of scale. So if I have a 6 on the Richter scale, and then if I have a 7 on the Richter scale, the earthquake at 7 is 10 times as strong as an earthquake at 6, or that kind of an idea. But it's not a regular scale, it's a logarithmic scale. So let's sort of lead into why we need logarithmic functions, or why we need the idea of a logarithm. Remember back we talked about inverse functions, and for a linear function we saw that to get the inverse of a linear function we simply exchange the x and the y values, and then we would solve in this case for y. And that was an important thing. We wanted to solve the equation for y, and then we could talk about it being a function. Now if I have an exponential equation like this and I interchange my x's and y values, I come up with sort of an exponential function, or an exponential equation anyway, that has a variable up in the exponent. But how would I change this to y is equal to something? Like, I can't divide by 2 because this is an exponent, it's not 2y. So I don't have any tools at this point in time where I could rewrite this as y is equal to. And so somebody invented the logarithmic function, which says that to solve for y you do this. You say the exponent is equal to the logarithm of base 2 of this value x. Or in other words, and we'll look at how we read this in a sec too, in other words, 2 or y is the exponent to which 2 must be raised in order to get x. Y is the exponent to which 2 must be raised in order to get x. It's looking at things quite a bit different than things we've seen before, but we'll practice that a little bit. So one of the things that we want to practice, and we'll do more of this later, is changing equations from an exponential form like this, or exponential notation, to a logarithmic notation. Let's throw some numbers in there. So here we have 100 is equal to 10 to the x. In just looking at that, I know that that has to be 2. X must be 2, because 10 squared is equal to 100. However, if I was to change this to logarithmic notation, it would be x is equal to log base 10 of 100. Or in other words, x is the exponent to which 10 must be raised in order to get 100. You could read it this way. Log base 10 of 100 is equal to x. Or the exponent to which 10 must be raised to get 100 is equal to 2. Again, in this case, the answer, of course, is 2. They must be the same because we switched their form. it's very critical that you understand and are good at switching things from exponential notation to logarithmic form and back. Because as we're solving logarithmic equations, this will be a powerful tool that we can use. Here's a few definitions or kind of rules of the road that we have to worry about with logarithms. First, a logarithmic function is defined as the inverse of the exponential function. We've seen that. The logarithm bases that we can use, we're restricting them to only be bases that are greater than 1. Not equal to 1, but greater than 1. Another sort of rule that we have to live by is that you cannot take the logarithm of a negative number. Your answer to the value of a logarithm can be negative, but I can't take the log of a negative number. For example, log base 2 of negative 5, I can't do that. But to what exponent must I raise 2 to get 1/8? The answer is negative 3. Sure, that works, because 2 to negative 3 is equal to 1 over 2 to the positive 3, which is the same as 1/8. In this case here, log base 2 of minus 5, I can't do that because we'll just see. Log base 2 of negative 5, let's make that equal to, say, x. So let's change this from log form to exponential form. The base is 2, the exponent is x, is equal to negative 5. So my question is there any way that I can raise 2 to some power and get a negative number? There's no way. If this is a positive number up here, of course I'm not going to get a negative number. Even if this is a negative number, as I've seen over here, I don't get a negative value of the expression. I simply get a fraction with a positive exponent. And so there's no way I can get a negative. So I cannot take the logarithm of a negative number, but the value of a logarithm can be negative. So here's how we can read them, and we've done a little bit of this already, but this is how I'd read it. The logarithm base 2 of 8 is equal to 3. That's sort of the official way to say it. The logarithm base 2 of 8 is equal to 3. Or we can also say this. The exponent to which 2 must be raised in order to get 8 is equal to 3. I also like to say 2 raised to the third exponent, or to the power of 3, gives me 8. Okay, so the exponent to which 2 must be raised to get 8 is equal to 3. So let's take a look at that, and just looking at that definition. To what exponent must I raise 2 to get 32? Try that. I think it comes out to 5. 2 to the 5th should be 32. To what exponent must I raise 5 to get 125? I think it's 3. To what exponent must I raise 4 to get 64? I think it's 4. Oh, there's no base written on this one. If there's no base, we assume it to be a base 10. To what exponent must I raise 10 to get 100? Right, answer's 2. Ooh, this is an interesting one. To what exponent must I raise 8 to get 2? Let me write that out. To what exponent must I raise 8 to get a 2? Well, it can't be 1 or 2 or higher. It must be a fraction. If I raised 8 to, say, the 1/3, or in other words the cube root of 8, sure enough that'll come out to 2. So the value of this one would be 1/3. So you may have to deal with fractional exponents or radicals, but we've seen those in the past. So as I said earlier, one of the things you want to be very good at is converting from exponential to logarithmic and back. Here's a couple. So 10 squared is equal to 100. I know that's a true statement. If I wanted to convert that to logarithmic form, this is how I do it. And there's various ways to do it, but I often start with just the word log, so log, and then I look over here to see what the base was. The base was 10, so I put that as my base here. The value will be this other number, 100, is equal to the exponent is 2. The value of any logarithm is always equal to an exponent. So log base 10 of 100 is equal to 2. often we call this 10 here our base, we call the 2 our exponent, and for lack of a better word, we call the 100 our value. So if that helps you sort of move things and arrange things in the right order, that will. Also notice I've color coded this so you can follow the colors where all the colors go. Here's another example. 5 to the minus 4 is equal to 1 over 125. Gee, I don't think that's right. I think it should be 625. Anyway, if I was wanting to convert this then to log form, I write log. Okay, my base is a 5. My value is this over here, 1 over 625. Let's put it in brackets so we don't get them mixed up. Is equal to, the value of any logarithm is equal to an exponent. Let's try going the other way. Here we have logarithms, and we'll convert them to exponential notation. Focus on the base. Here's 4. The exponent up here, value of a logarithm is always equal to an exponent, so this must be a 2, is equal to the other number or the value 16. Do this one, base is 10, the exponent is 5, is equal to 100,000. Okay, so practice that, going from exponential to logarithmic and back. As we'll see in another section, in solving logarithmic equations, this is an invaluable tool to be able to switch back and forth. In one case it might look like an insolvable question, but when you switch it to the other form, suddenly it's easy to solve, and vice versa. Now, one concept that we haven't talked too much about before, and is the idea of a number e. In logarithms and exponential functions, it turns out that there's a number e that seems to pop its head up all of the time. Just as an analogous kind of letter or number to e is that of pi. Pi we know is 3.141592, and it just keeps going. So it's an irrational number, goes on forever. And we know that it's a relationship between the circumference of a circle and its diameter. They always come out to this irrational number. Now the number e, when we deal with exponential and logarithmic functions, is a similar kind of number. It seemed like it always popped up in certain circumstances. And the number e is, let me just write it down here, 2.71828, and then it just keeps on going without repeating on forever. Some people, I think, have got it up to 100 billion digits now, and it doesn't keep repeating. So it's a number similar to pi, but it's a number we use when we're dealing with exponential and logarithmic equations. And it appears so frequently that we created a button on our calculators for it. Notice that on your calculators you do have a log button, and the log button on your calculator is base 10, but you also have a ln button on your calculator. And the ln button, as I've indicated here, is the same thing as a logarithm base e. So when I take the log of something using base e, I call that a natural logarithm. Okay, so those are some sort of basic understanding or basic definitions, ideas of logarithms. One other problem that we run into is that our calculators only deal with logarithms base 10 and logarithms base e, or ln. So sometimes we have to find out the logarithm of an expression that has a different base. So for example, I may want to find out what the logarithm, say base 7 of 49 is. Oh, well, now that's an easy one, because it's to what exponent must I raise 7 to get 49? Well, the answer is 2. I could just do that in my head. But what if I went log base 7 of 50? I look at that and I go, well, it's got to be 2 point something, but I don't know what that something is. Well, we can figure that out exactly using a nice little handy formula called the change of base formula. And the change of base formula says this, is that I'm taking the logarithm of some base of a product. Oh, and here I've got this indicated wrong. Let me switch it up. this one should be on the bottom, and this one should be on the top. There. So if I'm taking the logarithm of any base of something, of some value, and if this b isn't on my calculator, what I can do is use a change of base formula that says take the logarithm of this value and divide it by the logarithm of that base. Notice here they popped up a new letter a, and that letter a is any base that we choose. We could choose any base. Of course, though, we're going to choose the bases that are on our calculator. We're going to choose either log base 10 or log base e, which is the same thing as ln. Now, it seems a little confusing, but once you've done it once or twice, it's not bad. So let's say, for example, I need to go log base 7 of 50. My change of base formula says all I do is take the logarithm of the top number and divide it by the logarithm of this base. And I get to choose whatever base I want in there. I choose 10 because it's on my calculator. To solve this then, all I do is go log on my calculator, log 10 or log 50 divided by log of 7. And I'll get 2 point whatever the number comes out to be. But that's a change of base formula. Very handy, especially if you're taking the logarithm with a base that's not 10 or e. Those two I have on my calculator. 7 or tons of others I don't. Change of base formula helps me with that. Okay, so here would be a practical example of using logarithms. So say for example I have a solution in which its hydrogen ion concentration is this, 2.45 times 10 to the minus 3. If I wanted to find the pH of that solution, I would simply plug it into my formula. My formula is hydrogen ion, so I'd plug that number in right there, times 10 to the minus 3, and I would figure out what my pH would be. It's probably around 2 or 3, somewhere in that range. But you can do that on your calculator and solve that. Now, turning our attention just quickly to a graph of logarithms. Here's what the logarithmic graph looks like. Notice that if I were to do an exponential graph, here's an exponential graph, it goes up like that, something like that, that this graph is the actual, or is the exact inverse. So if I was to draw a line straight through here, something like that, let me move things around just a little bit so it looks a little bit better, right about like that. So if I drew this line here being y is equal to x, we know that inverse functions reflect on that line. So if I was to look at any point along here and look at the distance between here, between my exponential and my logarithmic graph, I would find that they would be the same distance away. So a logarithmic graph looks like this. It starts over here and it comes up. Well, it doesn't have a little angle on it. And it goes up this way. And it keeps going on forever. Notice that it doesn't cross this y-axis. And like we said before, I can't take the logarithm of a negative number. So x being negative, I can't do that. That's why there's no values here. Now, if I wanted to transform the log function, I could do that with formulas. So I could make the thing go up, or I could make it down. With transformations, I can go left, or I can go right. I could do a reflection on the x-axis, or I also could do a reflection on the y-axis. So the same kind of transformations as we've seen with numerous other functions. So today we've talked about the general idea of what a logarithm is. We found that it's the inverse of an exponential function, and that there's a number of ways that I can deal with those. And it's handy to deal with a logarithmic function because it allows me to say y is equal to something. Whereas if I got the inverse of an exponential function, I had y in the exponent and I couldn't get it out of that. But I can get it out of the exponent if I use the logarithmic function. And we've seen that it's important for us to be able to change from exponential notation to logarithmic notation. We've seen a quick example using pH, and we've also just briefly looked at the graph of logarithmic functions.